This is the Day 5 homework feedback. Useful if you want to see the kinds of things that get full credit and also to get my advice on places where you could save time or follow what somebody else has tried out. This is the number 1. It's about how does an animal excrete excess NH3 ammonia. And this person did some advanced circles, probably on some kind of touch screen, and then hand wrote with a stylus for the rest of them. So let's zoom in. They've shown all the important pieces here. I'm going to number them. That's what I'd recommend that you do. The thing that drives all of this is the proton pump here, which uses an ATP to move a hydrogen, H+, in. But the events that started all off, where I'll number the beginning, are here, where NH3 moves freely or fairly freely across membranes. And once it's in, it can easily leave. So that's what this blue is showing. Once it's in, it can easily leave. But if the NH3 interacts with a proton, it forms NH4+. It's charged and it can no longer cross the membrane. Charged molecules, ions, don't easily cross membranes. So we could have argued that instead of putting the 2 here, maybe we want the 2 here, where where the proton pump is pumping a proton in. That's providing the protons for this, and that gives us NH4+, which 6 cannot cross the membrane. Now, would you need the same numbers? Not at all. You could have done 1, 2, 3, and 4, and I would have known it. You probably could have done 1, 2, and 3, and I would have understood what you meant about the order. The numbering can help you make sure you've gone logically through it with no missing steps, and I've been seeing significant numbers of missing steps on the homeworks. What about the labels? This person labeled this a proton pump, but this is a proton pump. Doesn't really need the label for me anyway, because there's the proton. You should add in the things that are useful for you. What about contractile vacuole? Well, I was telling you in the question about what this was, so you didn't really have to. This is by context, it's really clear that that's happening as a contractile vacuole. So next step, we've got this NH4 in there, and with NH4+, it's charged, so we're going to get a hydration shell around it. Water's going to be attracted. Each one you add in is going to have multiple water molecules around it. So if we put in an aquaporin, this is an aquaporin, then water will be attracted because waters here will be trapped in a hydration shell. They are not free to go back out. And so waters come in for every NH4, more NH3 gets converted to NH4, and you get more and more water, and this vacuole swells. Then later over time, you wind up with a setting where it fuses. That's this set of lines here. Fuses with the membrane to form a pore. There's actually a set of proteins that arrange all that stuff. And you lose whatever free protons there are, not very many because most of them will be tied up with ammonia and the water. And that excretes both this waste ammonia and waste water. In lots of animals, there's no problem actually with just letting a lot of protists, there's no problem with just letting the NH3 diffuse out across the membrane. They don't actually need the contractile vacuole with the ammonia in it to get rid of water. But you need to excrete this anyway. If you excrete it this way, if you're a freshwater animal, you can get rid of all that water you've been taking in as you feed or just through osmosis that you need to get rid of. Now, did it really need all 3 sketches? This one probably could have been done with 2, or I'll even show you some where 1 is enough. In fact, this next one does it with some images and then some text. Again, I'll number them as we go. So we've got 1 NH3 entering, 2 the proton pump here, bringing in these H pluses. Here's the ATP and ADP that are powering it. That is converting. I probably would have put an arrow up to these NH4s, but you don't really need them because by context, that's clearly what's happening. And those NH4s are then attracting a hydration shell. This would have been a good spot potentially to actually write hydration shell or abbreviate it around all these positive charges. So that's going to bring in water through, and I often draw these as two circles. What I really mean is it's a donut. Here's the donut hole in the middle. That's the little channel where the water goes through in the aquaporin. So that's going to accumulate a lot of water. It's, as long as you keep adding NH4s, you're going to get more and more water in, and eventually it's all excreted. So let's get back to the numbers. We've got 3, 4, the hydration shell, 5, that's going to attract in more and more water. Eventually it's going to fuse, and 7, all these leave. This person added some text for it. As NH4 plus and H plus concentration increase, H2O will follow. Large vacuole will fuse with the membrane to excrete. Okay, so they did it all in one sketch because they put those changes over time over here. They really didn't need that many words. I would have understood it, and it would have been really clear with less than that. Second question was about approximate cause for the sodium-potassium pump creating a concentration gradient. There were two ways to interpret this. One is what's going on at the molecular level of a cell. And this person put in a variant of what I went through in class, showing the binding sites, something I would have sped up. Instead of showing the bilipids here and drawing them over and over and over, I would have just done 2 lines. Anytime you do 2 lines around what is clearly a protein, that tells me you mean this is the bilipid membrane. And if you only meant 1, you would just do 1, but 2 means it's 2, a bilipid. They've shown the binding sites, then they've redrawn it to show it with sodiums. Got an ATP nearby, stuck a phosphate on here. Here it is still in the same conformation with the sodiums that came in from the inside. Then we're going down to here. With the phosphate on, it changes conformation. So it's gone from this conformation closed at the top to, and so it's now closed at the bottom, and the sodium has no way to go but out. And then we bring in new potassiums. Phosphate is still here. Lose that phosphate. And we go back to this state, and the potassiums, I think they're showing them going here, which would have been the outside of the cell, but I'm pretty sure they mean it's closing here. And, oh, sorry, no, they've got it right there. They are binding potassiums here. Nope, they've got it on the wrong side. So the potassium should be going out this way, not here. And then we go back, so this is where the potassiums have left. And we can start over. So this makes a point. You can make an error like this. I didn't actually notice this one at the time, but conceptually this was all the stuff I wanted to see. You can make an error like this, and it's a good reason why you want to go back and check your understanding. You can show things to me, or you can just check to make sure it really makes sense. In this case, this person would easily have figured it out, because if you look back, here's 3 sodiums, and here's 2 potassiums, but we know it's got to be 2 potassiums in, 3 sodiums out. And I think this person clearly understood this well enough to know that, so it would have been an easy check to make, that the potassiums leave once we go back to this conformation closed at the top. And here's another version of question 2. So we've got, so this was the mechanism of the individual pump proteins. And then the other way to think about it is at the whole cell level. And one reason I'm showing you this is that on an exam, I would have accepted either version. They both show a deep level of understanding, and they're both consistent with the wording of the question. So this person put in the sodium-potassium pump. Here's 3 sodiums out, 2 potassiums in, takes an ATP. That gives you high potassium inside and high potassium outside. Again, if you wanted to number it, you could go 1, 2A or 2, 2B or 3 if you wanted. I'm not too concerned about the sequence. And then for a lot of this potassium, it's built up in high concentration, but you have potassium leak channels. So this potassium is going to tend to leave just because it's in high concentration, even though the membrane is going to get more and more negative. This person hasn't put that in yet. That's coming. So potassium can leave here, and so we're constantly recycling the potassium, but higher concentration of potassium inside, and then we're recycling the sodium, but higher concentration sodium outside, and the sodium, this we're going to get back to, is the ultimate cause. Having this concentration gradient of sodium with minus charge inside means sodium has a high tendency to enter, and you can use it to bring in glucose, amino acids, and other molecules, even against a concentration gradient. So you can concentrate things, or you can use antiporters to get rid of things against a concentration gradient. So secondary active transport, because each of these takes ATP, but the ATP was used here in creating the sodium concentration gradient and the negative charge. Okay, so back to this person. They then pointed out 20x potassium, 10x sodium. So, and you can just think of it as about 10x for each. It's not a big deal. And then that leads to the equilibrium for potassium is minus 100 millivolts. Equilibrium for sodium is plus 50. So why doesn't it go to the equilibrium for potassium? Well, because some of the potassium is leaving, so it won't be minus 100. If you take out some of that positive charge, it's going to be more positive. Sorry, I said that wrong. It won't be minus 100, even though this potassium is leaving, because you always have some sodium coming in, and that positive charge coming in will make it more positive than minus 100. So minus 70. So why doesn't it go to plus 50, the equilibrium for sodium? That's because you're always getting some potassium leaving, and there's more potassium leak channels than there are ways for sodium to enter, and so you're closer to the minus 100 equilibrium for potassium than you are the plus 50, so minus 70. And I probably should be calling it resting potential. It is an equilibrium of sorts, but more commonly we say the resting potential of the cell is minus 70. Okay, so third one was, what's the ultimate cause for sodium-potassium pump? An ultimate cause is an evolutionary reason, usually. Sometimes it's historical or something like that, but usually we're talking about what was it selected for. It creates a concentration gradient because cells benefit functionally from the gradient. Didn't actually need to say that. Could have just gone to say the concentration gradient with the pump allows sodium to travel down the gradient, and this is both charge and concentration from outside to inside, so it's an electrochemical gradient. Electro, because of the charge, chemical, because of the concentration, while carrying valuable molecules with it like glucose, and that's in these transporters known as secondary active transport. So all cells need that sodium concentration gradient and negative inside, although it's not always minus 70 and the concentrations aren't all the same across all cells. They all need it for secondary active transport. Here's another version. In this case, the person gave an example of secondary active transport, sodium moving down its concentration and charge gradient, bringing with it glucose, amino acids, and so on. And also said this in words. Another version, you can pause it and read through this if you want. And this person included these pieces to show how it works, but here's the ultimate, the value of it, the ultimate cause, why it's selectively favored. Number 4 was what causes the equilibrium potential. The resting potential. I keep saying equilibrium. And I prefer to use resting potential. So here is some background. We've got some sodium coming in, which makes it more positive. We have some potassium leaving. Positive leaving makes it more positive outside. In other words, there's less positive. That makes it more negative. So those two forces are in opposition. Sodium making it more positive, potassium leaving making it more negative. Typical animal cell winds up being around -70 because of those two events. And then I like the fact that this person drew the sodium-potassium pump really small because, yes, this is what causes the concentration gradient, but it's the balance of these two forces that take us to -70. Why -70? Well, the equilibrium for sodium is +50 at the particular concentrations, about a 10-fold concentration. So 10 times more sodium outside. That would tend to drive sodium in, just because of the concentration. When it's +50, that positive charge repelling sodium balances the greater likelihood of sodium reaching that channel, and you wind up with no net movements, equilibrium. For potassium, higher potassium inside, but there's more of it, so some tends to leave, makes it more negative. The equilibrium is -100. That's when the negative charge is able to hold in the much higher number of potassiums. So the balance is between those two, and the balance could be right in the middle if we had the same amount of sodium, entering as potassium leaving, then we'd be halfway in between +50 and -100. That would be -25. But more potassium is leaving. There are more ways for potassium to leave than sodium to enter. Another way that I like to describe it, high potassium, high sodium. If we were at 0 millivolts, sodium would keep entering until the inside is +50. If we put in potassium channels, then potassium would leave until the inside was -100, holding in that excess high potassium on the inside. Put that together, sodium-potassium pump, creating the concentration gradient, sodium entering. The one thing I would change here is that this is secondary active transport, so don't need this. The sodium enters, and potassium leaving, but there's more potassium leaving greater than the sodium active transport rate. So the equilibrium is the resting membrane potential is closer to the equilibrium for potassium. So all these were full credit. Here is another one. This is a minimalist answer. This one had explained the other things about the sodium-potassium pump and the different concentration gradients in question 2 as part of question 2, so they didn't need more of it here. And they just pointed out, here's the two forces, sodium entering, potassium leaving. And so between the two, there's more of this. So you're closer to equilibrium for potassium. And here's another one, going through the same thing. And what I wanted to show you is multiple ways, all full credit for these. And I forgave sometimes skipping one particular thing, but I do want you thinking about, am I missing any steps? So not everybody talked about the -100 equilibrium for potassium alone and the +50 equilibrium for Na+ alone. And I just accepted that it was inferred by the text and the images that they showed. 5 was calcium transport. And there are multiple types of gated calcium channels. This is a calcium-gated calcium channel. That's the kind that we think is in paramecium. And in those cases, calcium interacting with the calcium channel will pop open that gate. There are also voltage-gated calcium channels. So schematically, a voltage-gated calcium channel in the membrane. You can think of it as having a plus charge here. So if we brought in sodium, That positive charge would repel that gate. It would open up, and now calcium can enter. They're also ligand-gated calcium channels, and those are all part of the toolkit that you can use, and we'll talk about all of them through the course. So here's our calcium. There's the gate, and it's a +2, so you could imagine it's positive, and when the calcium binds, that repels the gate on a hinge. It opens up. So calcium can enter when it's open. That'll keep happening as long as it's in this conformation. We'll talk a bit more about it later, but calcium-gated calcium channels seem to close because they have more than one binding site for calcium. And when this additional binding site binds, that actually causes a conformational change that closes the channel. So it'll open in a response to a pulse of calcium, a little bit of calcium, but as calcium increases, you get more binding at the other sites and the gates all start to close. That gives time for the calcium pump, ATP dependent, it's primary transport, primary active transport up to pump the calcium out. Calcium pumps are slower than a channel. So if you want something to happen quickly, use a channel. All you have to wait for is the channel to open and stuff to come in. Slower, this requires you got to get an ATP there, you got to get a calcium there, you got to wait for this change, all those different steps. So pumps are slower than channels. And eventually calcium binds to the gate again. So this is the second site and causes it to close. And here they're showing the second site for a calcium-activated calcium channel. Here it is all in words. I won't read it, but it all makes sense and explain what's going on. So doing it in words, I'm okay with if it's really clear to you what's going on. I would guess that for most of you, this printing these neat words is going to take longer than these simple sketches to show what's going on, but I'm okay with words. Number 6. This was a paramecium bumping into an object. That is one that opens a stretch channel. This is just physically open. You strain that membrane and it pulls it open. Sodium enters. That sodium gets to positive charge. It doesn't actually need to bind. It just needs to be nearby. If there's a positive charge on this calcium channel, that'll pop it open. You get calcium in. In fact, what happens is this calcium channel is real near the anterior. So you get a pulse of calcium in here, and that actually spreads and seems to open calcium-gated calcium channels. That spreads all the way through. Regardless, you eventually get calcium to these binding proteins at the base of cilia, and that causes the cilia to reverse the direction. So now they're beating the other way, and they're going to back up our paramecium. They were going this way, now they're going this way. That's going to back up our paramecium. The backing is going to continue until the calcium pumps pump out enough calcium. Once they're restored to the low levels, the calcium's not bound to those calcium binding proteins, and we move back to going forward. There's fairly recent data that I saw just a couple years ago that there seems to be a similar mechanism that causes reversal of the beating of direction of cilia in mammalian, including human, respiratory systems. So I don't know that that's been confirmed, but it's basically what I would have predicted. It's basically same mechanism. Now this took 1, 2, 3, 4, 5, 6 sketches. Here's somebody who did it all in one. They added words, but the words could have been a lot simpler. In fact, could have probably completely skipped all the words except maybe some labels. Stretch channel. Didn't really need to say that's a calcium pump, so just stretch. Maybe some indicator of time here, and that's all the words. So probably none of this was necessary. So all the steps are here. Here is 1, opening the object, 2, sodium in, 3, positive charge opening a calcium channel, 4, here's the calcium, 5, the calcium binds, 6, we reverse the direction, and over time, 7, the calcium gets pumped out, it's out, and we stop the movement. So just that and a few words would have been sufficient.